Okay, so hey guys, today I'm going to be lecturing on section 3.5 from your textbook. And this is going to be a section on graphs. We've talked a little bit about graphs previously in this chapter, actually, when we were talking about pictorial representations of relations. And in those particular graphs, we had edges that had arrows to them, and so they were digraphs. Here, we're going to look at graphs which are a little bit more general. They're just called a graph, so they're not a digraph. There's going to be no directionality to the edges, and there's just going to be vertices and edges. And so graph theory, which is basically what this section is trying to introduce you to, is a pretty important branch of mathematics. And so this is a very rudimentary sort of introduction. It's a branch of mathematics with applications to many fields such as chemistry and computer science, social science, linguistics. And one thing to also note is that because it's such an important field, there's also a little bit of difference in how people communicate in the terminology of graphs. And so that's also something to keep in mind if you want to move forward in graph theory. Okay. So let's try to relate this back to what we do know about graphs. So remember, we drew digraphs when we were thinking about relations on a set A. And each element of that set A was a vertex. And then if they were related to each other, they'd have this directed edge to it. For us, in this particular section, we're not going to have directionality. Okay? So let's start with just the straight up definition. So definition. A graph, G, okay, is a pair. I'm going to write that pair VE of sets where V is a non-empty set and E is a set of unordered pairs of elements, of distinct elements, I should say. In V, of V. An element V in V is called a vertex, and an element, say, let's just say lambda in E, is called an edge. An edge between vertices U and V is denoted UV or VU. Okay, so this is this notation here, UV or VU, is oops, sorry about that. This notation UV or VU is understood to represent an unordered pair of vertices. So that's why it doesn't matter if you write UV or VU, because the edge representing that connection does not depend on how you order the vertices. Okay, so let me just write this. So UV is said to represent UV. Okay, so it's an unordered pair of vertices. Okay. And so One thing to note here is that this is called a simple graph, the way we've defined it. So a simple graph, the way we've defined it. Because a simple graph doesn't allow for loops, and also a simple graph has at most one edge between vertices, right? And in general, as and in particular we saw in the digraphs that we looked at when we were thinking about equivalence relations and partial orderings, vertices can have loops, but a simple graph does not allow it. And in general, graphs can also have multiple edges between the two same vertices, two different vertices, and there can be multiple edges between them. This definition does not allow for it, and because it doesn't allow for it, we call it a simple graph. Okay? And so let's start off with a really simple example of a graph. It's going to be kind of a silly example because, well, it's taken from the book, but it's kind of a silly. So imagine we have these 5 people, and let's say they're represented by the vertices. This one is Sneezy. Okay. This one here is Doc. And this one here is Happy. This one here is Grumpy. And this one here is Dopey. So we're looking at a vertex set consisting of different people, and how we're going to relate them, i.e. how we're going to connect them with edges, is to see, let's say these people are at a party, and we're going to connect them with an edge if and only if they had a conversation at that party. So let's just draw this out. So Sneezy talked with Doc and Dopey and Happy. Okay. Grumpy talked with Doc, and Grumpy also talked with Happy. Okay. Dopey talked with Sneezy, we already established that, but Dopey also talked with Happy. And I think that represents sort of what I want to see. So what can we extract from this? Doc talked with Sneezy, Doc talked with Grumpy, and no one else. And no one else in that particular party. Happy talked with Sneezy, and Happy talked with Grumpy and Dopey. Dopey talked with Sneezy and Happy, and Grumpy talked with Doc and Happy. And so this is what's represented in this graph. Note, that's all the information that is represented in this graph, is who are the people at the party, and which 2 people had conversations. So there's no spatial information here. So let me write that here. That's important. That is, we don't know what the relative positions of these people were at the party, where they were standing when they talked. We don't know why they didn't talk. We just know that if there's an edge between them, they talked. And if there's not an edge between them, they did not talk. Also, one thing to note is that this is not a unique way that this can be represented here, right? So I can just as well draw the graph in the following way. I can put Happy down here, and I can put Dopey up here, and then Sneezy over here, and Doc over here, and Grumpy over here. Now if I connect the edges, it might look a little different than from the previous slide. So let me just go back. Previous slide, notice how it looks. But it still contains the same information because Dopey talked with Sneezy, Sneezy talked with Doc, Doc talked with Grumpy, and yep, I think that's it. I think that's all the information. And so this graph here actually contains the same information as this graph right here. It's just a different way of picturizing it. And so that's kind of interesting too. I mean, you can play with this. You can try another orientation, right? So for example, you could also do, let me just draw a little line here. You could also do Sneezy up here, Dopey somewhere here, Happy over here, and there's no reason to draw the lines straight either. You can feel free to draw however, you can draw them however you please. It's just, I think, appealing to our brains if they're straight. But for example, you can draw them like this, right? That's an edge between Sneezy and Happy, and then Sneezy and Dopey, and then Dopey and Happy, and then Happy also talked with Grumpy. Grumpy talked with Doc. Sneezy talked with Doc. Okay. So these two graphs here and the graph I drew on the previous page all contain the exact same information. So this exercise is to illustrate that you don't really need to worry about how you draw the information as long as you draw the information. And what is the information that's being conveyed is that here are the set of vertices, and here's how here's the ones that are related, and the ones that are related are connected by an edge. Okay. So now, with that in mind, we call two graphs. So V1, E1 is going to represent the first graph, and V2, E2, right? We call them as isomorphic. Okay? If and only if their vertices are the same up to renaming, and we'll see what I mean by this except for renaming statement in the next example. And whenever there is an edge in E1 joining two vertices, there is a corresponding edge in E2. Okay? So now let's look at an example. The following graphs are isomorphic. So these are isomorphic. So B, A, C, D, okay? Let's say the graph is as follows. And then, so that's one graph. And next I'm going to do alpha, beta, gamma, and delta. And all these are going to be just vertices. And so alpha is connected to beta, beta is connected to gamma, beta is connected to delta. And third, you could also have a graph, say, down here. So I'm going to put A, and then B, and then D, and then C up here. So A is connected to B, B is connected to D, and B is connected to C. So all these graphs might look different to you, but they're, again, actually the exact same thing. It's just, again, it goes back to that conversation example we started this section with. We've drawn the graphs in different ways, and we've just given the vertices different labels. So we can notice we can make a connection between A, capital A, alpha, and little a, but then you can also make a connection between B, beta, and little b, and C, gamma, and little c, and then D, delta, and little d. So for example, you see that in the first graph, capital D is connected only to capital B. Similarly, in the second graph, delta is only connected to beta, and little d is connected only to little b. And so these graphs are isomorphic. Okay? So really there's no right answer. If I want you to draw some sort of graph that has certain properties, you can have fun drawing the edges and things however you please, as long as it's right. Okay, so some more definitions. So let G be a graph, okay? The order of that graph, so the order of G, is the number of vertices, i.e. the cardinality of the set V. Or not the cardinality, but rather, yeah, the number of elements in the set. Yeah, right, okay, the cardinality, the number of elements in the set V. The size of G is the number of elements in E. Okay. Vertices U, V are adjacent if and only if there is an edge connecting them. The edge UV is said to be incident with U and V. The degree of a vertex is the number of edges incident to it. And lastly, a vertex is isolated if and only if it has degree 0. Okay. So just back to our previous example, just draw this again right here. So in this particular example, order equals 4, size equals 3. Okay? So B is adjacent to A, B is adjacent to C, and B is adjacent to D. A is not adjacent to D, and D is not adjacent to C. Okay, because there's no edge connecting them. The edge BC is incident to B and C, and so on and so forth. The degree of A is 1, the degree of D is 1, the degree of C is 1, and the degree of B is 3, because there are 3 edges containing B, basically. and there are no isolated vertices in this particular example. Okay, one sort of subtlety to discuss now is that, note, it's possible that E is empty. Okay, so in that case, you get graphs like this. So when so, you get graphs like this. Okay, that is in particular every vertex. When the set of edges is empty, every vertex is isolated. Okay. Now, sort of the opposite end of the spectrum, a graph in which every distinct pairs of vertices are adjacent is called a complete graph. Okay, and so just some properties about this. If G, a graph, has order n, that again, remember, means that there are n vertices, then every vertex has a degree n minus 1. The complete graph with n vertices is denoted K sub n. Okay? So K sub 1 is just the point. K sub 2 is going to be the line containing those 2 points. So there's just 1 here, 1, 2. K sub 3 is this little triangle thing. But again, remember, I'm choosing to draw in this way, but you can draw it in any other way that captures the same information. And so on and so forth. Let's just draw one more. So 1, 2, 3, 4. So you can, right, so so this is K4. And so maybe one thing you can try is to draw K5. What does K5 look like? Okay. And now we motivated all these definitions to talk about this next very important sort of fundamental result. So that fundamental result is motivated by the following. So, for example, let's look at the complete graph. Actually, let's not look at a complete graph. Let's look at this sort of our favorite example again. Let's go back to this example here. And so let's write the degrees. For A is 1, for B is 3, for C is 1, and D is 1. Notice if we add these together, we get 6. And that might not seem interesting to you, but in particular what I want to mention is that 6 is an even number. And indeed, when you add up all the degrees of the vertices in a graph, you will always get an even number. So sum of degrees of graphs is always even. And why is that? So the way to think about this is like if you imagine a bunch of people in a room shaking hands, then the total number of handshakes that must have happened is even. I know that's a bad example in this time of coronavirus, but I mean the example itself still holds. Okay, so now let's make this rigorous. We have a theorem. And part A of this theorem is the handshaking lemma. The handshaking lemma. For every graph G, right? The sum of the degrees is even. Sum of the degrees of the vertices. That's not quite the statement. Sum of the degrees of the vertices is twice the number of edges. Okay. Thus, the sum of degrees is even. And B, for every graph G, the number of vertices of G having odd degree is even. Okay, so just take a second to digest what that's saying. Is if you if you look at all the vertices of a graph and you see that some of them have odd degree and some of them have even degree, the number of vertices that have odd degree is always going to be even. Okay, so let's go ahead and prove this. So first, part A, and this is actually quite straightforward. It's because each edge is incident with two vertices. So the sum of the degrees of the vertices is exactly twice the number of edges. Okay, so the sum is even. B, so obviously the sum of the degrees of the vertices that have even degree is an even number, right? Because we know that, right, if you add up okay, let me just write this down. So the sum of the degrees of vertices that have even degree is even. That makes sense, right? You add a bunch of even numbers up together, it's going to be even. If the number of vertices with odd degree were odd, then the sum of the degrees would be odd. And this contradicts the handshaking lemma. So this contradicts the handshaking lemma. So there must be an even number of vertices with odd degree. Okay. For the complete graph Kn, so remind yourself what Kn is, each vertex has degree n minus 1. And so if you add all these together, you get that the sum of the degrees is n times n minus 1. So this is sum of degrees. And now because this number is twice the number of edges, n times n minus 1 divided by 2 equals number of edges in Kn. And if you're really super sort of nerdy, this actually also equals 1 plus 2 plus 3 plus all the way up to n minus 1. Okay, that's just an interesting tidbit. Okay, so now that we've sort of developed the terminology of graphs a little bit, we can continue doing that. So much like the idea of a subset of a set, you can define a subgraph. So the graph v prime e prime is a subgraph, okay, of VE if and only if V prime is a subset of V. So remind yourself what it means for a set to be a subset of another. And E prime is a subset of E. So that is, we can create a subgraph of the graph VE by taking some points in V and then some edges from V. It's understood that the elements of E prime are taken, so they are incident to elements of V prime. So it doesn't matter, it doesn't make sense to take edges out of E which aren't incident to the vertices of V prime. And so it's understood when I retake a subgraph that the edges in that subgraph are incident to the vertices in that. So for example, again, back to our original graph, right? So here's the full graph. Let's say this is G. Then G prime, for example, could be the bad graph. Right, so I've taken the vertices BAD out of G, out of the set V that comprises G, and then I've taken the edges that are incident to those vertices. Notice what I mean by saying what it's understood about how we take the edges is that I didn't take BAD and then take the edge connecting B and C, because that wouldn't make any sense. Okay, now some more definitions. A walk in a graph G, okay, is a finite sequence of vertices, so V0, V1, Vm, where Vi plus 1 is an edge in G. Okay? The walk is said to traverse the vertices in the sequence. So that is, in this walk up here, V0 through Vm, the walk traverses V0 through Vm. Starting with initial vertex V0, okay, and ending with terminal vertex Vm. The length of the walk is M, the number of edges in that walk. If Vm equals V0, the walk is closed. Okay. And now we get a special definition. A path in G is a walk where all vertices except maybe initial and terminal, vertices are distinct. So a path is a special type of a walk, and then this is all just terminology. So closed. So closed just means you start and end at the same point. Okay. Okay. So let's look at an example now. So I'm going to draw a graph here. It's going to have 6 vertices. 3, 4, 5, 6. The edges between 1 and 6, 1 and 2, 6 and 5, 5 and 4, 4 and 3. Okay, so we get this nice little shape out here, but then 2 is connected to 5, 6 is connected to 3, and 3 is connected to 5. Okay, so that's the graph here. So here are some sequences from this graph. Okay, so for example, P1 could be 6, 3, 5. P2 could be 1, 2, 5, 6, 4, 3. P3 could be 3, 2, 5, 2, 3. P4 could be 2, 5, 3, 4, and P5 could be 1, 2, 5, 4, 3, 6, 1. Okay, so why did I do these? So notice, so P1 here is a walk, okay, and indeed it's a path, but so this is a walk. The initial vertex is 6, the terminal vertex is 5, length is 2, and I'd like to now maybe think about why the length of that is 2. So it's a walk because there's an edge from 6 to 3, and then an edge from 3 to 5. The length of it is 2. What else did we cover in that definition? The initial vertex is 6, the terminal vertex is 5. It's not closed, and indeed it's also a path. This is not a walk. P2 is not a walk. Because I've listed a sequence of vertices, and there is an edge from 1 to 2, and there is an edge from 2 to 5, and there is an edge from 5 to 6, but there is no edge from 6 to 4. There's no edge from 6 to 4, and so that this is not a walk in this particular graph. Okay? P3 is a closed walk because I've started and ended at the same spot. P4 is what? P4 is a path of length 3. And indeed, P1 is also a path. 2, 5, 3, 4, path of length 3, and P5 is closed path. Of length 6. Okay? And so this could represent a lot of different things. For example, this could be a flight map between 6 different cities. Yeah, it could be a flight path between 6 different cities, and for example, let's say a salesman needs to travel to all 6 of these cities, but he or she lives in city 1 and needs to get to all of these cities. He could take the path P5, go to 2, 5, 4, 3, 6, and then 1, and he would want to come back to 1 because he would want to come home. Now, because the graphs we're talking about are all finite, i.e. the vertex set is finite, we have the following theorem, right? Let G be a graph of order n. If there is a walk from V to U in G, then there is a path from V to U. And B the length of a path in G that is not closed is at most n-1. The length of a closed path is at most n. And I'm not going to prove these because they are kind of intuitive, but for example, the way you would prove A, which is if there is a walk from V to U in G, then there is a path from V to U. So remember, the difference between a walk and a path is that the intermediate vertices that construe a walk could be repeated. And so basically, you find a walk from V to U, and then you basically remove all the repeated elements, and you found a path, right? And so that's why if you have a walk, you have a path. And then if you have a finite set of vertices, then part B basically follows from that. Yeah. Okay. And so now what we're going to have we're going to sort of put an eye towards is relating graphs back to this idea of equivalence relations and so on and so forth that we talked about earlier in this chapter. So let G be a graph and U be a vertex of G. Okay. The vertex U, sorry, not the vertex U, the vertex V is reachable from U if and only if there is a path from V to U, or U to V, I should say, from U to V, from U to V. the number of edges, in a path of minimum length from U to V is called the distance. From U to V. And we denoted with this d u v. And a subtle point here is that for any vertex u, duu equals 0. Okay? That's just a subtle point. Now for an example. So consider a graph with the following vertex set: A, B, C, Q, E, F, G, H, I, J. Okay, this is an odd example because, they use basically the letters A through K except for D, and it's because D, again, is used to represent distance. And so let's say the graph is drawn in the following way. Not C here, rather there's F here. So we have this graph here, and then we have C, Q, H, G, K, and J. K, G, and then we have E and I. So let's say the graph is this graph right here. Okay, so we can think about the distances between each of these vertices, right? So, for example, DAF equals 1, DQQ equals 0, DJQ, what does it equal? What does DJQ equal, you think? 1, 2, 3. 1, 2, 3. It's 3, right? Because you always want to find the minimal path between the two vertices, and that's just A to G, G to H, and then H to Q. You don't want to go by a K, or you don't want to go, D, G, K, H, C, Q, right? It's long. So D, G, H, Q. So D, G, Q is 3. And for example, if you're super curious, D, A, Q is undefined. Okay. So again, I motivated this as an example because we have these sort of 3 different pieces to this graph. And if you notice here, we have point J is reachable from Q, G is reachable from Q, C is reachable from Q, E is not reachable from Q, E is not reachable from H, I is not reachable from A is not reachable from G, but G is reachable from H, and G is reachable from Q, and so on and so forth. And so we have this nice little sort of almost a partition, you might say. So you have this partition between these vertices and these edges in this graph here. That's going to motivate the following definition. So here's a definition now. Let G be a graph. Okay. If U is a vertex of G, the component containing U is the subgraph and we're going to denote it CU. CU, whose vertex set consists of vertices reachable from U. Okay, and whose edges are what? Are all the edges incident to those vertices. Okay, so this is super messy here. So edges incident to those vertices. Okay. So if you look back at the graph on the previous page, you notice that what are all the vertices that are reachable from B? It's A and F, and so the set of vertices reachable from B and the corresponding edges is equal to the component containing A, and that's equal to the component containing F. Similarly, from the previous example, the component containing E is the component containing I. And then to finish this off, you have the component containing Q is going to be equal to the component containing C. It's going to be equal to the component containing H is equal to the component containing G is equal to the component containing K and equal to the component containing J. Yeah, K was the one before. And this idea that they kind of seem to form a partition is the exact idea that allows us to define a particular way of defining an equivalence class on graphs. So notice, because B is reachable from A, the components containing B and the components containing A are equal. So that kind of goes back to the idea that if any two equivalence classes have any points in common, that they must be exactly the same, right? And notice if they have no points in common, they are, like, if it looks like they have different points, then they are completely disjoint, right? So E is reachable from I, B is not reachable from A, but it's not a case that B might be reachable from E and A is not, right? Because the component of B and the component of A are the same. And so that motivates the next theorem here. So theorem. Let G be a graph with vertex, sorry. Set V and let R be a relation on V with U is all related to V if and only if V is reachable from U. Then R is actually an equivalence relation. Sorry about that. R is actually an equivalence relation on V, and the equivalence classes are the vertex sets. Of the components. And so we want to prove this now. So how do we prove this? So if we're trying to prove something is an equivalence relation, what do we have to prove? We have to prove the relation is reflexive, symmetric, and transitive. Okay? So, reflexive, yes, because every vertex is reachable from itself. And this stems from the way that we've actually defined distance in this particular setting, because remember the distance from any vertex to itself is always 0. So symmetric, I'm not going to prove symmetry, I want you to think about it, but this is actually pretty obvious. And transitive, this is actually also obvious. So let's say there's a path from U to V and from V to W. Clearly, there's a path from U to W. Okay, so the relation on a graph saying two vertices are equivalent if and only if they have this, if and only if they're reachable from one another, is an equivalence relation, and the equivalence classes are the components containing those vertices. Okay. Now some more definitions, and we're actually getting pretty close to the end here. A graph G is connected if and only if every vertex is reachable from every other vertex. Otherwise, G is disconnected. So, for example, Kn is connected for all natural numbers. Okay. The graph that we talked about on the previous page, or maybe two pages ago, 3 pages ago, Jesus. So here's a graph here that is not connected because the subgraph ABF is sort of complete. So A, there's no path from A to I, for example, or from B to Q, right? Okay, so that's a disconnected graph. Now another point I want to take is sort of building on from this idea of connected and disconnected, is to go back to this graph here. And so notice here that if I look at the subgraph of this graph, so BAF, which is that subgraph, that's a connected subgraph of the graph that I'm sort of looking at. So the overall graph is this big old thing right here, right? This whole big old thing is the overall graph. And if I take a subgraph, this BAF, it's a connected subgraph. But if I add any other vertex from this subgraph, so let's say I want to take this subgraph right here, but if I add any other vertex, my subgraph will no longer be connected. And so this gives rise to the idea of a maximally connected subgraph. So definition. Let G equal VE and let G prime equal V prime E prime with, G prime a subgraph of G. Then G prime is a maximally connected subgraph of G if and only if G prime is connected and for every subgraph G double prime whose vertex set contains V prime, G prime, double prime is disconnected. Right? Okay. And we're going to finish off with this following theorem. For each vertex V in a graph G, let CV be the component of V in G. Then CV equals CW if and only if W is reachable from V. And this follows immediately from the idea that these CVs, these components, are the equivalence classes. B, CV does not equal CW if and only if no vertex is in both CV and CW. And again, this follows immediately from the equivalence classes. So it's a partition. Remember, equivalence classes form a partition of a set, and if they have any points in common, they must be completely equal, and otherwise they're completely disjoint. For each V, CV is connected. And lastly, for each V, CV is a maximally connected subgraph of G. And you want to prove this, you can prove this, but all of this follows from definition of CV and from the fact that the components form equivalence classes. Alright, so that's it. That's our little rudimentary lecture on graphs. I hope you enjoyed it. Subscribe to the channel if you enjoy my abysmal lectures, but otherwise I will see you again at a later time with another lecture. Okay, thanks. Bye.